a moment. Can you wait?
Ok. Possiamo fare un attimo allora questo, vediamo se si riesce. You tell me when I can see. Okay. Good morning, everybody. Today we will spend the day together, and the subject of our day will be density functional perturbation theory, and in particular the calculation of the phonon spectra. So we will see how you can use the Quantum Espresso software to calculate the phonon dispersion, and we'll also tell you something about thermodynamics and what you can do with the phonon frequencies that you obtain. We will have a laboratory in which we will see the calculation of the phonon dispersion of silicon, and also you will see the calculation of the thermodynamical property, the vibrational energy, free energy, entropy, and also of the temperature-dependent volume of silicon and thermal expansion. So, what is this all about? This will be the first lecture. So in the first lecture, we will see the definition of phonon, and we will see a small introduction to the crystal lattice dynamics. Then we will see what is a density functional perturbation theory and how you can use it to calculate the dynamical matrix of a solid and its phonon frequencies. And then I will give you a brief introduction on why this method might be convenient with respect to a more direct frozen phonon calculation. And so we will have a few ideas on how to calculate the dynamical matrix at finite Q. This will depend on time, but you will find here, if you want, all the detail on how you can transform a calculation that apparently require the calculation of a big supercell by doing a calculation on one unit cell of the solid. So let's start with the definition of a solid. I think now you have already seen this part several times. So what we want to study are the small vibration of the atom about their equilibrium position. So we assume that we have a solid where the atomic position are given by Ri, and basically are given by Bravais lattice vector that I call R mu, plus the position of the atom inside the unit cell. So R mu, as you know, is a Bravais lattice, and this means that this index mu is 3 integer, n1, n2, and n3. and that this is N1A1 plus N2A2 plus N3A3, where A1, A2, and A3 are the primitive vector of the Bravais lattice. And I think that you have already learned how to define in PW a primitive vector, so a Bravais lattice, and how to give the size of the unit cell. So in one unit cell, we assume that we have n atoms, and that this index S goes from 1 to the number of atoms in one unit cell. And also, these are input coordinates of PW, and you know how to give the coordinate of the atom inside the unit cell. So just to fix the idea, it is useful to focus on a subset of the solid. So to consider N1 cell in the direction A1, N2 in the direction A2, and N3 in the direction A3, so that we have a total of N1 times N2 times N3 unit cell. And then we use Born-for-Karman periodic boundary condition. So what happens after N1 cell is the same that what happened in the initial cell. Obviously, we can think that we do the limit where this n goes to infinity. But it is useful that we focus on a given n, because in this way we have a well-defined number of degree of freedom, and basically we are focusing on n times n atoms in the unit cell, in the solid, in all the solid. And let's say that we call omega the volume of one unit cell, and V the total volume of the solid, that is n times omega. So basically, to describe our problem, we introduce the displacement of the atoms from their equilibrium position. We assume that the atom makes a small oscillation about this equilibrium position, and we introduce a variable, a vector ui for each atom that depends on time, and that gives the instantaneous position of the ions as a function of time. Clearly, this is a three-dimensional vector for each atom of our solid, so we have a total of 3 times n times number of atoms degree of freedom. And basically, our problem is to set up some equation for this displacement and to solve them. So you know that within the Born-Oppenheimer approximation, the nuclei moves in a potential energy surface that is given by the total energy of the electron calculated in the instantaneous position of the nuclei. So, for instance, within density functional theory, you can get the total energy of the atom once you have decided which are the instantaneous positions of all your atoms at time t. And if you can calculate this function, basically you can set up an equation of motion for the nuclei. And at the beginning, we will consider a classical problem and write the classical equation for this displacement. The hypothesis that these displacements are small, let us do a second approximation that is an approximation that we will use always in this lecture, that is the so-called harmonic approximation. So instead of using the complete function E tot of the nuclear position, we expand this function in a Taylor series about the equilibrium position. So we write that this is E tot indicate with this parenthesis all the atomic positions. So then we have the first derivative of the total energy with respect to U, E, and alpha. Should sum over E and alpha. Alpha is the x, y, and z coordinate. And then plus 1/2 the sum over E alpha and J beta of the second derivative of the total energy with respect to d U E alpha, d U J beta, U E alpha, U J beta. And now these derivatives are calculated at U equals 0, so at the equilibrium position. And now we make also another hypothesis that we have relaxed our system, so that we have already minimized the energy in such a way that the forces on the atom are 0. So we assume that there is no forces acting on atom, and that we are at equilibrium with the atomic positions. So basically, the potential energy on which our ion moves is known if we are able to calculate the second derivative of the total energy with respect to 2 atomic displacement. Atomic displacement that can occur also in different cells. So if this atom is in the cell closest to the origin, this atom can be several cells of distance. And so we can set up an Hamiltonian for this problem. We can write, we can introduce the momentum of the ions, the mass of each ions. Basically, this index E, as I wrote here, is an index of the Bravais lattice and of the atom inside the unit cell. But clearly, all the atom in different unit cell with the same S have the same mass. So actually, this is a mass that depends only on the S index of the atom. In all the unit cells, we have the same, for the same S, we have the same mass. So our Hamiltonian is the sum over I of and alpha of pi alpha squared divided 2mi plus 1/2 sum over E alpha and J beta of the second derivative of the total energy with respect to U E alpha, U J beta, U E alpha, U J beta. I have not written the first term because it does not depend on our variable ui. It is a constant. If you want, you can put it here, but then it will not enter into the following derivation. So now we have to write the equation of motion, and we know the Hamilton-Jacobi equation. So pi alpha is the derivative of h with respect to du E alpha, and U E alpha dot is the derivative of h with respect to d I alpha, and this one has a minus sign. Okay, so we can do this derivative starting from our Hamiltonian here. This is simple because P appears only here. So this is pi alpha over mi, the derivative with respect to time of the displacement. And this is minus, we have to do the derivative of this. Here, E alpha, be careful, appear twice. It means that these two will not appear. So we have sum over J beta of second derivative of E dot over du E alpha du J beta u J beta. And so we obtain our a classical equation of motion. Well, we can write pi alpha equal mi u dot. So mi second derivative, well, let's say d over dt twice u e alpha is equal to minus the sum over j and beta of the second derivative of E dot over du E alpha du J beta u J beta. So now you see this is a very big linear system. It is a set of differential equations. And basically, we have 3 multiplied by n multiplied by n atom differential equation. Is a very big system where every variable, in principle, is coupled with every other variable because it is true that this interatomic force constant decreases with the distance, but in principle, if you move an atom in one cell, you feel there are forces even in a distant cell. And you know that we can simplify this kind of equation exploiting the translational invariance. So trying the solution in the form of a phonon. So we introduce a vector Q that is a wave vector, and we try the solution in the form of a plane wave. So we write that the displacement. Now I reintroduce the symbol mu, s, and alpha of t. I write it in this form. I write that the displacement in the atom mu is given by the displacement in the initial unit cell S alpha of Q. I will call this of Q because every Q will have a different displacement, but this is not the index mu. It is the displacement in the first unit cell. And then I put an exponential e to the I Q r mu. So in each unit cell, I will have a displacement in the first unit cell multiplied by this phase factor. The time dependence will be minus e omega of q t. And then I will also put a 1 divided square root of ms. This will simplify the following equation, so it is useful to keep it there. This square root of the mass. And since this is a phase, in principle, this displacement here can be also complex, but this is a real quantity. It is the real displacement, so I have to take the real part of this term. That means this plus the complex conjugate. And so if we now insert, well, let's study a little bit what does this thing mean, at least at t equals 0. At t equals 0, let's see what we are doing. Well, suppose that I take q equals 0. So I take the gamma point, the so-called center of the Brillouin zone, the gamma point. Then this phase e to the I q r mu is always equal to 1. Here there is an example where you see a chain that is the simplified view of a solid where there are two atoms in the unit cell, the blue one and the red one, that repeats after a period A, repeats periodically. Well, when Q is equal to 0, it means that if this is the displacement in the first unit cell, the one closest to the origin, in the other unit cell, you have always the same displacement. So basically, you are displacing one sublattice with respect to the others. If we take a Q vector, so a reciprocal lattice vector of this lattice here that has periodicity A is 2 pi over A. If we take a Q that is at 1/2 of 2 pi over A, that is on the border of the Brillouin zone, then you see that this phase, e to the I QR, is 1 in the first cell, -1 in the second cell, 1 in the third cell, -1 in the fourth cell, and so on. So it means that if I have this displacement in the first unit cell, I will have the opposite displacement in the second unit cell. The same displacement in the third, the opposite in the fourth, and so forth. This means that if I want to describe this kind of displacement, I would need 2 unit cells of my solid, because the new solid repeats periodically after 2 unit cells. And the same if I take 1/4 of the 2 pi over A, then in the first unit cell this phase is 1, then I, then -1, then -I, and after 4 cells I recover the same displacement as the original vector. So for a Q like that, I will need a unit cell that is 4 times my original unit cell to simulate this phonon. Clearly, one can think also to some wave vector that are incommensurate with the lattice, for instance, square root of 2 divided by 4. And in this case, the pattern never repeats. But with this technique, we will be able, also in this case, to calculate the second derivative with respect to a phonon like this. Okay, so now we can insert our solution on our phonon solution on the equation of motion and see what happens. So we should insert it here. You see, the real part means to take this plus the complex conjugate and divide by 2. But the complex conjugate has a time phase that has a plus sign here. So what happens to this part and to its complex conjugate, all the complex conjugate term will be multiplied by phase factor e to the plus e omega t. And then we will have a term with e minus omega t and one with e plus omega t. And the two separate, so the two coefficients separately must be 0. So we write the equation just for the term that have minus e omega t. And the other will give the complex conjugate equation. So we insert it here. This is ms, 1 divided square root of ms. So the second derivative means that we have to do the second derivative of this, and means with respect to time, and means that we brings down minus e omega q to the square. us alpha of t e to the I q r mu. And this is the the first term, then this is equal to sum over J and beta of the second derivative of the total energy with respect to U mu S alpha. Let's call the J nu S prime and beta. So we said that J is nu and S prime, and I is mu and S. And here we will have 1 divided square root of ms prime, U S prime beta of Q, e to the I Q are nu. And then there is both here, e to the I minus I omega qt, and here e minus I omega qt. The two simplify. So here we have the square root of ms. Minus e, minus 1 to the square is 1. E to the square is minus 1. So this gives minus omega square. US alpha of Q. And then the e to the IQ are mu. I bring it in this, in the first. Here there was a minus. There was this minus here. And so here we have minus sum over J and beta, e to the minus e Q are mu. That was this one. And then this term. Here I would have square root of ms, but I bring it here. So here I have square root of ms and ms prime. Then I have the second derivative of the total energy with respect to U S alpha, mu S alpha, U nu S prime beta, U nu S prime. This e to the minus e plus e q are nu, and U S prime beta of Q. And this sum over J is basically a sum over nu and S prime. So this 2 minus, we can put a plus. And we end up with our equation of motion. So we can define the so-called dynamical matrix. So the dynamical matrix of the solid is this. The sum over S prime and beta, we keep it here. And we sum over mu, the phase factor, the second derivative of the n. Oh, by the way, I've not said before, but maybe I have to say it. This second derivative of the total energy with respect to 2 atomic displacement, you see, if you displace only the atom J in the direction beta, this and makes a unitary displacement, this gives the force that acts on the atom I in the direction alpha. And for this reason, these objects are called the interatomic force constant. And so in the dynamical matrix, we have the interatomic force constant, the square root of the masses, and the phase factors. So we define this. It depends on Q. It depends on S, S prime, alpha, and beta. And it is a sum over nu of square root of the masses, e to the minus I Q r mu, the interatomic force constant, we thought U mu S alpha, U mu S prime beta, and the phase e to the I Q r mu. This is our most important result so far. You see what happened. We had a big system where three number of atoms per unit cell variable were coupled. And now we have found an eigenvalue equation. So we can rewrite this kind of equation now like this. Omega square Q U S alpha of Q equal to the sum over S prime and beta of d S prime alpha beta of Q U S prime beta of Q. So we have found an eigenvalue equation. We have to diagonalize this dynamical matrix. But now the number of variables that are coupled are 3 multiply the number of atoms per unit cell. It is true that we have a different equation for each wave vector Q. And in principle, we have a number of unit cell wave vector Q. So the point is that we have factorized this very big equation into a several much smaller equation, one for each Q. One point, you see that here there was an index mu. And in principle, I would have, and here I've added only on nu. So in principle, here there might be some dependence on mu. But you have to think that here we are summing over all the vector of a solid and looking to one particular atom. If we change the atom and again sum over the atom of the unit of the solid, this thing cannot change. So basically, for each mu, this thing is always the same. So here I have not written a dependence on mu. And basically here I could take mu equals 0, for instance, the unit cell closest to the origin. And so basically the program of today is this. We have, with density functional perturbation theory, find an expression for the dynamical matrix. We have to do it once we have chosen a Q vector, a wave vector, and then we diagonalize this dynamical matrix and find the frequencies as a function for that wave vector Q. And in principle, we have also the eigenvector of the dynamical matrix. If we want the displacement, we should put the eigenvector here, divided by the square root of the masses, and put this phase. Clearly, the dynamical problem is completely defined once we give the initial position and the initial velocities. And the final result will be a linear combination of all this particular solution with coefficients that depend on the starting conditions. But at the moment, we focus on the calculation of the eigenvector of the dynamical matrix, this object U, and the frequency of the phonon omega Q. We can put an index nu if you want to, let's indicate with lambda, just not to confuse. To say that at each Q, we have 3 multiplied by the number of atom frequencies, and this index count these different frequencies. Okay, so our idea now is we take the expression of the total energy of the electron gas given by density functional theory, and first learn how to calculate the derivative of this total energy with respect to 2 different parameters that we'll call lambda and mu. For instance, And once we have learned how to calculate the second derivative with respect to two generic parameters that enter in the Hamiltonian, we can do this, use this formula and find what is the expression for the dynamical matrix. So, let's start from density functional theory. I will use a simplified version with respect to the one that is really implemented, but not really. I mean, it contains already many of the difficulties that one finds in the real problem. So let's see how it works. And here we keep just the definition of the dynamical matrix and our equation of motion. So the total energy of DFT is written here in the case of a local external potential. So we don't consider non-local pseudopotential that would add a practical complication, but just a local potential. So the formula will be simpler, but already gives you all the ideas of this thing. So it has a kinetic energy term that, so we are in the Kohn-Sham picture where we have the kinetic energy of the non-interacting electron gas. These phi are the one electron wave functions. I think you have seen this already in the previous lectures. There is a kinetic energy term, an external potential that couples with the charge density rho, and then the Hartree and the exchange and correlation energy. Let me write them like this, that depend on rho, and the ion-ion interaction. The charge density is the sum over the occupied eigenvalues of the square modulus of the wave function. And, well, we put an index 2 if we want to sum over the spin. So if you sum here and you consider a different state for different spin, you will not have these 2. If you do the sum over spin already, and these are only the occupied bands in a non-magnetic system, here you have a 2. Let's put this 2 that is in the papers, so just not to make different formula. And basically, once you have the density, you can calculate the Hartree and exchange and correlation energy and the interaction of the density with the local potential. So you have already seen, I think, the Hellman-Feynman theorem that says that if I want to calculate if this energy depends on some external parameter, and in particular the ionic coordinate will be in the local potential, so we assume that the local potential depends on this parameter, lambda and mu, and so on. Well, then the first derivative of this total energy with respect to one of these parameters, dE tot over d lambda, that are the forces that you have already. If lambda are the atomic displacement, these are the forces. And you have already seen that this can be calculated with the unperturbed charge density. So with this density, the density that minimize this function, it is equal to an integral over all the volume of d v log over d lambda rho of r d3r. So basically, this term is not much more difficult than this to calculate. And the forces can be calculated after a self-consistent run. And then we have the derivative of the ion-ion term. Now we need instead a second derivative of the total energy, and one simple way to obtain this second derivative is to derive this another time. So we derive with respect to a parameter mu. And this has a term that is the second derivative of the local potential with respect to mu, to lambda, and to mu, integrated with the charge density. And this, again, is not much more difficult than the term that appear in the forces or in the total energy. But then there is another object. We have to derive this term. We have the derivative of the local potential with respect to lambda, multiply the derivative of rho with respect to mu, d3r, plus the second derivative of the ion energy with respect to mu and lambda. And this is the difficult part, because a new object appears. It is the so-called induced charge density. We have to know what happens to the charge density when we move an atom, and to calculate its first order derivative for this atomic displacement. So this is the difficult term, the one that will keep us occupied for this lecture. How can we calculate the change of the charge density induced by an atomic perturbation? Well, to write the expression is not difficult. We take this definition of the charge density and we make a derivative with respect to mu. So, maybe I can write up here. So the derivative of rho with respect to mu is equal to twice the sum over I, d psi star over d mu psi plus psi star d psi over d mu. So basically the ingredient that we need is the change of the wave functions with respect to a parameter mu. And this is an ingredient that is not in the self-consistent calculation. It's a new ingredient that we have to find a way to calculate. So how we do it? Well, we can use perturbation theory. We start from the equation satisfied by phi and make an expansion with respect to mu of all the variables and look at first order which kind of equation we obtain. So we write the Hamiltonian. This is the equation that you obtain minimizing the total energy with respect to the one electron wave function, right? The one that gives you the equilibrium density. And now we think that both the wave function, the eigenvalues, and the Kohn-Sham potential depend on the parameter lambda. So the Kohn-Sham potential depends on the parameter lambda because V Kohn-Sham is defined as the local potential plus V Hartree plus V exchange and correlation. The local potential depends on the parameter lambda. The Hartree term, you know, is the integral of rho over prime divided r minus r prime, d3r. And the exchange and correlation potential, d3r prime. And V exchange and correlation is the derivative, functional derivative of the exchange and correlation potential with respect to rho. both these two objects depend on rho. So if we do a perturbation, not only the local potential, but also Hartree and exchange and correlation will change. And so all the Cornish-Sham potential, in principle, depend on the parameter mu. And we expand these quantities to first order. So we write okay, I will rewrite later the eigenvalue equation if needed. So let's say we write the phi I of R and mu as phi I of R and 0 plus the derivative of phi I over d mu of R and mu calculated mu equals 0 multiplied by mu. Epsilon I that depend on mu will be epsilon I of 0 plus the derivative of epsilon I with respect to mu, calculated for mu equals 0, multiplied by mu. And V Cornish-Sham of R and mu will be V Cornish-Sham of R and 0 plus the derivative of V Cornish-Sham with respect to mu calculated to mu equals 0 multiplied by mu. And so if we insert this into the Cornish-Sham equation and keep the term at order 0, we'll give again this kind of equation. At order 1, we'll give the new equation for the derivative of epsilon I with respect to psi. So let's put this inside there. We will have minus 1/2 Laplacian square plus V Cornish-Sham of R 0 plus the V Cornish-Sham over the mu multiplied by mu multiplied psi plus d psi over the mu multiplied mu equal to epsilon I of 0 plus d epsilon I over the mu multiplied mu psi of R 0 plus d psi over the mu multiplied mu. So the order 0 term is this one, multiply phi I 0, epsilon I phi 0. And this simplify because at mu equals 0, the wave function will satisfy this equation. So we are interested in the term linear in mu. So if here we take the 0 order Hamiltonian, I can write here. Minus 1/2 Laplacian square plus V Cornish-Sham of R 0. And here we have d psi over d mu multiplied by mu plus dv Cornish-Sham over d mu multiplied phi I of R 0 equal to, and here we have d epsilon I over d mu psi of R 0 plus epsilon I d psi over d mu. Here there is, okay, the mu we can remove everywhere, and this is over mu calculated mu. Okay, let's say this. Let's write like this. So if we bring this, the first term, and this, the second term, we rearrange this equation as is usually found. That is minus epsilon I d psi over d mu is equal to minus dv con sham over d mu ci var plus d epsilon I over d mu ci of r. See, yes, if sometime I wrote the partial derivative, actually they are total derivative. So far we have not yet introduced partial. Sorry. You can think partial if you think that they depend on many variables. We are integrating with respect to one variable here. We are deriving with respect to one variable here. Okay. And now you see that this is a linear system. Basically, it is a linear system where we have a right-hand side that this contain this change of the Kohn-Sham potential with respect to mu. dV Kohn-Sham with respect to mu. That is dV log with respect to mu plus dV Hartree with respect to mu plus dV exchange and correlation with respect to mu. And since V Hartree now is no more written, but dV Hartree with respect to mu, Hartree depends on mu through the density, so it is 1 divided R minus R prime, d rho over d mu. And again, the critical variable is the change of the charge density with respect to the parameter, and the same dVxc over d mu is the functional derivative of Vxc with respect to rho, d rho over d mu. So once we have the change of the charge density with respect to mu, we can calculate the change of the Kohn-Sham potential with respect to mu and set up the right-hand side of this linear system. But in order to have to calculate the change of the charge density with respect to mu, we need the change of the wave function with respect to mu. So we need the solution of the system. So basically, this is a self-consistent problem, exactly as in the DFT. You have a Hartree and exchange and correlation potential that depends on the solution, on the wave function. Here you have a linear system where the right-hand side depends on the solution. And in principle, you can set up a self-consistent scheme. You start with some guess of the change of Hartree and exchange and correlation potential, obtain the change of the wave function. From the change of the wave function, you find the change of the density. From the change of density, the change of Hartree and exchange and correlation, and then you can restart the iteration. You have a new guess for the Kohn-Sham potential, and you can iterate this until you have self-consistency between the change of the wave function and the change of the change of Hartree and exchange and correlation potential that produced those wave functions. Basically, you check, once you have the new Hartree and exchange and correlation potential, you check that the difference with respect to the one that you used to calculate the wave function is smaller of a certain threshold. There is, however, a problem in this point, that this system is ill-defined. And I've not discussed how to calculate the change of the eigenvalues with respect to the parameter. Well, there is a simple solution for all this. Well, the fact why it is ill-defined is because suppose that you expand this solution d psi over d mu, you expand it in the basis of the unperturbed wave function of the Cone-Sham potential. You can write like this, Cj d psi over d mu. In particular, in this sum, you should sum over all the occupied and empty bands. All the state, the solution of the Cone-Sham potential are a complete basis for the space. But you see that on the eigenvalues, on the wave function Ci, this term gives epsilon I. And this is epsilon I minus epsilon I. So from this, that is 0. It means that from this linear system, you cannot get the projection of the change of the wave function on the wave function itself. Well, there is the lucky case that this piece of the change of the wave function is not needed. Actually, we can rewrite the change of the charge density considering only the projection of this wave function on the conduction state. Only the part in the conduction band, how the wave function change, the part that here contains the state, the conduction state, is important for calculating the change of the charge density. The part in the valence does not enter in the problem. And so we can limit the problem to the calculation of the projection in the conduction band of this change of the wave function. Let's see how this works. Basically, we can write, if we write Psi, and sum over all the state, valence and conduction, this is an identity. These are the unperturbed states. And I can write this as the sum over on the occupied state that I indicate with V. This I call projector in the valence band, plus the sum in the conduction part that I call projector in the conduction band. PC plus PV is equal to 1, and if you want, PC is 1 minus PV. So let's now insert here PC and PV, and let's see which term we obtain. So we have the rho over the mu equal to 2, sum over E. We put here PV d psi over d mu complex conjugate psi plus psi complex conjugate PV d psi over d mu. Plus twice sum over I. This I is just on the occupied state. And here I have to put P conduction d psi over d mu complex conjugate psi plus psi star P conduction d psi over d mu. So here I have a PV plus PC, and this is the identity. And here PV plus PC, this is the identity. So I've not modified anything. But now I want to show you that this first term is 0. So that we can write the change of the charge density due to a perturbation only with the projection in the conduction band of the change of the wave function. Well, let's write the expression of CV. So this is equal to twice sum over E. And here we can write like this, Psi of R, the scalar product between, let me call this Psi J, and sum over J, where J now is still occupied state. Or as before, let's write this CV d Psi over d mu, plus I have this complex conjugate, Psi plus Psi star CV of R CV d Psi over d mu. Plus the term with the conduction part. Now I focus on this because I want to show that this is 0. Let's take the complex conjugate here. And note that here I have E and V, but also E is a valence state. We can call this J. And here J. And simply here exchange E and J, because they are only dummy name for the occupied state. So in this first term, I want to put this E, and J. So this is equal to twice sum over E and J. I have a Psi complex conjugate of R that I have also here. Here I change E and J, so this is a J. So then I have a Psi J that I can put outside. Psi J of R, it is this and this. And here I have the complex conjugate of this. So here I have the Psi J over mu Psi plus this term, Psi J d Psi over d mu. And you see what is this? This is the derivative with respect to mu of the product Psi J Psi. But you know that the wave function, the solution of the Kohn-Sham problem are orthogonal. So this is equal to delta Ej. If I do the derivative of a number, it's 0. So this derivative is 0. And this term in the valence do not contribute. So we remain that the change of the density with respect to mu that we are interested in is can be written just in terms of the projector on the conduction band of the change of the wave function due to the parameter. And this is an important result because now here we can put here a projection in the conduction state. Put here a projector in the conduction state and put here a projector on the conduction state. So since this is a valence state, if we project in the conduction, this is 0, and so we don't have to worry about the change of the wave function with respect to a perturbation. And this projection in the conduction band commute with the Hamiltonian. So basically we end up to have it here. It commutes because if here you have a state Cc, when you apply the Hamiltonian to Cc, it gives the eigenvalues epsilon c Cc, and so you can exchange with this. And then epsilon c Cc is again the Hamiltonian applied here. And this is a number instead. And so you see, we can solve this problem putting a projector in the conduction band in the right-hand side. And this basically solves our problem, because now here we can add the term alpha PV, and to put this alpha in such a way that this term is never zero. And so the linear system becomes well-defined. The solution of a linear system, if in the right-hand side I apply a projector in the conduction band, will be already projected in the conduction band. And I can take this object and put it in the expression of the change of the charge density. And so, in this way, the linear system becomes well-defined, and the problem can be solved. Okay, here you have the demonstration that we have done already. And here, this is then, we can look here. This is the final form of the equation that we solve. There is a projector in the conduction band, the change of the Kohn-Sham potential with respect to mu that depend on the change of the charge density, the change of the charge density that depend on the solution of this linear system. So we have to iterate this linear system until we reach self-consistency. Okay, but now the problem is that we want to calculate the dynamical matrix and not just a generic second derivative of the total energy with respect to two parameters. And the dynamical matrix is written here. Yes?
Usually in perturbation theory, you have to apply a gauge to solve it. Where does that enter?
A gauge?
A gauge combined like transition and gauge design. There are different gauges that you have to impose in order to solve. So like to say that both of them are orthogonal when you get this. When you do the expansion in perturbation theory of the constraint, at some point you have to say that one is zero and to impose a gauge in order to impose that. And which gauge is best in the computational point of view?
Well, you see what we do here. Yes, what you mean is that you have to decide what to do to the change of the wave function projected in the conduction part, in the valence part. Sorry. What you see here is that this part is not entering. So the gauge is that whatever the one that you want to use. I mean, what enters here is only the projection in the valence band. We are not computing that part. I mean, when we put here the projection in the conduction band, that part in the valence is not computed, basically. The solution of this linear system is not inside this term. Yeah, I would say that this question, at this point, for computing the dynamical matrix, formulated in this way, this question do not enter. It enters in other questions, right, as computing the matrix element of R and these kind of things. But at the moment, here we have only the projection in the conduction state. And only when we calculate the matrix element of R, actually we are calculating always the matrix element between the valence and the conduction state. So I would say that this formulation is already independent of the gauge. It is already in a gauge-independent form, this thing. When I wrote the change of the charge density like this, This is already gauge invariant pair. Okay, let's continue. And let's see how we calculate the dynamical matrix. I will go slightly faster on this because it is a detail that is very important and is the reason for all this formalism. But I think that those of you that are interested can find in the notes all the detailed derivation of this. So what we have to do now to calculate the dynamical matrix is to take this expression of the second derivative and to put it in the expression of the dynamical matrix. And so the dynamical matrix, let me So this term here, inserted here, gives that d s prime alpha and beta of q is equal to, well, let's put in front of everything ms prime. So we have sum over mu. Let's put we have an integral of e to the minus e q r mu, second derivative of the total energy with respect to u mu s alpha. This second derivative have the second derivative of the local potential u mu s prime beta e to the I q r mu rho of r d3r. And here, in principle, I have to integrate over all the volume. And since we have seen that this term is independent on which mu we choose, basically we sum here over mu and divide by the number of cells. Because for each mu, it will give the same object divided, and so we divide by the number of cells. Plus, again, the same trick we do for the second term. So 1 divided by n, sum over mu and nu, integral of all the volume V of e to the I minus iq. This is r mu. R mu, dv log over d mu s alpha. And let's say that I put here the sum over mu. And I bring here the sum over mu, d rho of r, so d u mu s prime beta, e to the I q r mu, d3r, plus the part that derive, the dynamical matrix that derive from the ion-ion interaction. Good. And here we should, in principle, integrate over all our volume. And now the point that I want to make is that we can calculate, well, that here the charge density is lattice periodic. I want to show that this sum over mu and nu of this object is also lattice periodic. And so basically this integral can be done in and we can define the second derivative of V log with respect to du s alpha q du s prime beta q as that sum over mu 1 over n as of e to the I minus I q r mu, second derivative of the total energy of the local potential with respect to u mu s alpha mu s prime beta e to the minus c q r mu. And what I want to show is that this is a function of R that is periodic. It has the periodicity of the lattice. And so basically this integral can be written as an integral over one unit cell, and it becomes n times the integral over one unit cell because these are two lattice periodic functions. This function instead, the sum over mu of, let's say, dv log over d u mu s alpha e to the I q r mu. We can call this dv log over du s alpha of q. And I want to show you that this can be written as a phase factor EQR multiplied by a periodic function that I call the periodic part of dv log of us alpha of q. And the same for the charge density. So if I define the rho over du s alpha of q as the sum over nu, this is S prime beta, d rho over d u nu S prime beta e to the I q r nu. Well, this is again a phase factor e to the I q r multiplied by a function that is periodic with the periodicity of the lattice that I call d rho over du s prime beta of q, periodic part. And so you see, since here you have the complex conjugate of this dv log e to the s alpha q, this will have a phase minus EQR, multiply a periodic function. This one will have a phase e to the IQR multiplied by a periodic function. So this second integral can be written as the product of two periodic functions. The two phases cancel, and I can integrate over one unit cell and remove this n. And so basically I can calculate the dynamical matrix doing perturbation in this way. So calculating with perturbation theory only the periodic part of the change of the local potential and only the periodic part of the change of the charge density due to a phonon perturbation. Phonon perturbation meaning this. Yeah, so this is the final expression. We will have this dv log over dus, maybe here there is a complex conjugate, and no, this, I mean, it depends how you write in the definition. Probably this should not be here. The definition of this is this thing. I don't know if you want. You can define this with a star, as you prefer. I don't know in the paper how it is written. Sorry, there is a star here. That probably should not be here. Or you can write it. And then there is the product of two periodic parts of the function, and all of them are integrated in a single unit cell. So the claim is that you can calculate all these periodic parts of the wave function doing calculation in a single unit cell. So let me demonstrate this in one case, then the other are very similar. Let's start demonstrating that this object is a periodic function of the Bravais lattice vector, meaning that if here I add an R mu, I obtain the same quantity. And then I will show that this is a phase factor multiplied a periodic function. Well, how can we see this periodicity? Well, I cancel here. Yes, maybe in all the notation here there is a star. So it is defined like this. So why it is a periodic function? Well, V log of R is a sum over mu and S of some potential that depend on S of R. So it is a sum of objects centered in the difference. In the different atomic positions. So this second derivative is actually 0 if mu is different from nu or S is different from S prime. Because when I do one derivative, the term u s is in only one of these terms, and then I have to do the derivative with respect to the same atom. So basically, this is 1 over n, sum over mu and nu of delta mu nu, delta s s prime, of e to the minus e q r mu, vs of r minus r mu minus vs minus u mu s, second derivative with respect to u mu s alpha, u mu s beta. The direction can be different. And then here I have, again, I to the I q r nu, and nu must be equal to mu, so the two phases here cancel. I remain with an expression like this, and basically I can write this and remove this, and remove the 1 over. No, a delta. So the 1 over n remain. But then you see that this derivative is independent on which mu I do, and it is a sum over all the mu. So it is an object that is lattice periodic. For the second part, instead, this object, let's say that we want to demonstrate that this object has a phase factor multiplied by a lattice periodic function. We can calculate the Fourier transform of this. And if we see that the Fourier transform at a given k has only component when k is equal to q plus a reciprocal lattice vector, it means that it has a phase e to the iqr, and then a sum of a plane wave with a reciprocal lattice vector is a lattice periodic and will be this object. So what we have to do is to calculate the rho over du s prime beta of q instead of r, k, reciprocal lattice, that is 1 divided the volume, the integral over the volume of d3r e to the minus e k r, and then this thing, sum over nu of d rho over du nu s prime beta of r e to the I q r nu. And now we can exploit the fact that the rho is periodic in this way. So let's look at the rho of r. And suppose that we change the position of an atom in the cell 0, the atom S prime in the direction beta. So we do the derivative of u 0 S prime beta and look at the point r. Or we move the atom in the cell nu S prime beta, but instead of looking at the point r, we look at the periodic image r plus r nu. So if we move the atom r nu and look at r plus r nu, or move the atom in the origin and look at the point r, since the density is periodic, these two objects must be equal. So let's say that we put r prime this, and this will be r prime minus r nu. So here I can put the derivative with respect to the atom 0, provided that I put here r minus r nu. And now if I change variable in the integral, I put here r prime equal r minus r nu. So r will be r minus r nu will be equal to r prime. Means that r is equal to r prime plus r nu. So I can put here r plus r nu, and here r. I have to put the sum over nu in front. And so you see what happens here, that now there is r nu here, but not more in the derivative of the rho. And so I have a term that is sum over nu e to the I q minus k r nu. And this term is different from 0 only when q minus k is a reciprocal lattice vector. So let's say q minus k is equal to a reciprocal lattice vector G. Or let's call this minus G. So we have that k is equal q plus g. That is what we wanted to demonstrate. If k is equal to q plus g, this is different from 0. So the Fourier transform is different from 0 only when q is when k is q plus g. So basically, this object can be written like this. The rho over the u s prime beta of q equal to sum over g of the rho over the u s prime beta of q plus g e to the I q plus g r. And this is of q. So it is e to the I q r multiplied by a periodic function that is written in Fourier series, exactly as I claimed. Can go on a little bit. Okay. This we have demonstrated, and now we can see how this periodicity can be found in the expression of the change of the charge density in terms of the periodic part of the block wave function. So now we have to introduce, maybe I do not write on the blackboard, this part I go slightly faster, and we look into the transparencies. So now the index E in a solid is actually an index of the K in the first Brillouin zone, and a band index B. And through the block theorem, we know that the wave function are e to the I kr multiplied by a periodic function u kv. And moreover, we will use the time reversal symmetry. So we will use the fact that the block wave function at minus k complex conjugate are equal to the block wave function at k. So if we use this, then the expression of d rho over du s prime beta of q, well, maybe we write it down. Otherwise, I go too fast. So we wrote the rho over the u s prime beta of q equal to sum over nu of the rho of the u nu s prime beta, nu s prime beta, e to the I q r nu. And then we had written that this term was twice, so this is sum over nu of sum over K and V, the block state, PC dC K V over d mu S prime beta star C K V over let's say here we have e to the iq r. And then we have also plus psi kv star over pc d c kv over d u nu s prime beta e to the I q r nu. We can bring this inside the complex conjugate if we put a minus EQR nu, but and this is what is written there with the e to the minus EQR nu. But I want to apply this time reversal thing in the first integral. Instead of summing over k, I want to sum over minus k. So this will become a k star. And this will become a psi kv without the star. And so you see what happens, that this term is equal to this. And so I can write here 4 times the last term. So this is my expression of the charge density. E to the iq r nu. And now the point is that if I write, so I can put the sum over nu basically here. And if I write the block function so this is equal to 4 sum over k and v. Basically, u, k, v, the periodic part of the block function complex conjugate, e to the minus e, k, r. Then I have here this PC. Let me say, write the PC as a sum over k prime, some k. I have a psi kv prime v, or better, e to the I k prime r u k prime v prime of r. And then it is an integral in r prime, e to the I k prime r prime u k prime v prime r prime, integrated with this sum over nu of e to the I k r derivative of u k v with respect to u nu s prime beta e to the I q r nu. And now you can reason as before. Since ukv is a periodic function, you can write this sum over nu of E, Q, R nu, this derivative as a phase factor, E, Q, R, multiplied by a periodic object, the periodic part of this sum. So this will become, let's say, E to the I KR, E to the I QR, derivative of U K V with respect to U S prime beta of Q periodic part. And this is of R prime and has to be integrated with this. So you see, this is, these are two periodic objects. And so this integral will be different from 0 only when K prime is K plus Q. So we will have here just a delta, a phase K plus Q. And this K prime let's say that this object here all these things, let's say, I will write it like this: E to the I K plus Q R PC of K plus Q U du sorry no okay, correct, du K over du K S prime beta of Q periodic part, like this. All this object. And it will have a phase, it will have a periodic part and a phase K plus Q R. This phase K plus Q R cancel with this, E to the I K R with the K. Just the K will cancel with this. And we will end up with 4 E to the I Q R sum over KV U KV star of R PC K plus Q du K over du S prime beta of Q periodic part. And so you see that these are all periodic objects multiplied by E to the IQR. And so the periodic part of the charge, the periodic part of this thing will be this product of U KV star R multiplied by this. And for this object, we have to find an equation. And this equation can be found from our linear system. So from our linear system that is written like this, we arrived at this in terms of mu. If we now multiply by A to the IQ R nu, and sum over nu, basically we obtain this an equation like this where here we have the derivative with respect to Q with the same definition that we did so far. And this is the same object that was in the charge density, so it will become E to the I KR, K plus QR, multiplied by a periodic part, so the object that we have here in the charge density. And the only thing is to find what is the expression of the right-hand side here. So the expression of the right-hand side is dv con sham of r su du nu s prime beta e to the iqr. And since v con sham is periodic with the periodicity of the lattice, this, with the same reasoning as before, it is a phase factor EQR multiply a periodic part. The right-hand side of the linear system becomes like this, with the periodic part of the block function, the periodic part of the Kohn-Sham potential, the periodic part of the projector, and the phase K plus QR. So PC, deep C over the U e to the IQR mu, we have already seen is equal to this thing here. And so in the Hamiltonian, we will have the Hamiltonian between that phase EK plus QR, and we multiply the right-hand side, multiply e to the minus e k plus QR, so that phase disappears, and is found in front of the Hamiltonian. And define the Hamiltonian at k plus q as this object here with the two phases. And so this is the real linear system that we solve, h k plus q minus epsilon kv. The solution of the linear system that enters in the expression of the charge density, the periodic part of this change of the wave function, and this is the right-hand side. Okay, now the last point, the dv Kohn-Sham over the lambda has had this expression here. We have to put here the phase factor and the periodic part. So even in this, we multiply by e to the iqr nu and sum over nu. So here we will find the derivative with respect to the phonon amplitudes, these things that we have written so far, that has a phase factor, e to the ikr, and a periodic part. So we insert the phase factor and the periodic part everywhere, and we end up with this phase factor in the change of the R3 potential, and the periodic part of the change of the charge density. And this, I think, completes the demonstration. Well, the final formula are reported in the Review of Modern Physics, but also in the original Baroni, Giannozzi, and Testa paper, or the Giannozzi, the Gironcoli, and Pavone paper. Some detailed derivation is given in this paper that I wrote in 2001, also for the ultrasoft case, written in this more elaborated form, but really the result was here, except for the ultrasoft that was. So where this detailed derivation in some sense was needed. And this part will be instead for the next lecture. So I would propose to stop here for this lecture, and we will the next for the phonon interpolation and the thermodynamical properties. So we do the coffee break.